S1 and S2, welcome to BGE Physics Key Area 1, and we're going to be talking about space today. So you might be watching this video to catch up, to revise. Maybe you've been sick, maybe you've been ill, maybe you've just been on holiday. Who knows what's going on? But we're going to talk about revising the first section, part 1 of Key Area 1, and we're going to talk about space. I'm a physics teacher, so I love space. I love everything to do with space. I studied space, so this is going to be really fun. So let's jump in. So, what we're going to do, we're going to do 3 things: the solar system, space terminology, and telescopes, all right? Now, on page 5 in your booklets, you'll see that we have the word solar system, and that's what we're going to dive into first. And one of the first things we're going to do is show you a picture. Now, this is something you're probably aware of, all right? We've got the sun, we've got the planets, but there's other things in there that you maybe don't know. Things like asteroid belts, and things like Ceres and Makemake, and, well, I think you guys may know about Pluto, but some of you, I think roughly when you were born, Pluto was declassified from a planet into a dwarf planet, but we'll talk about that later. And we've got things like the Kuiper Belt and all sorts of stuff, but that should be fairly familiar to most of you. Now, we know that in the sun, we have 8 planets, okay? 8 planets. Now, the order of them is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, all right? And you can see that the further away you go from the sun, the bigger the distance is. That makes a bit of sense, doesn't it? Now, sometimes what you need to do is put a kind of, I think it's called a mnemonic, down here that helps you know the order of the planets. So my very easy method just speeds up naming, and that's going through the first letter of all the planets, and it's just a good way of remembering them in order, okay? So I think you know about the 8 planets, but as I just said, we now actually have dwarf planets. Now, dwarf planets are a little bit smaller. They don't quite make the cut to become a planet. And you'll see that we have Pluto is considered a dwarf planet that used to be considered a planet. Okay? So, that's dwarf planets. Now, there are also some more than just Pluto. Okay? There's more than just Pluto. We have something called Ceres. Now, Ceres is in the asteroid belt between Mars and Jupiter, all right? And it's actually fairly big. It's quite like a sphere, so it kind of almost looks like a little bit like a planet, but it's not big enough, and so we call it a dwarf planet, okay? And we have some other ones. They're slightly further out from the edge of the solar system, and it's called Haumea, Makemake, and Eris, along with Pluto as well. So that's some things you might not have known. Now, we also talk about these things called satellites. Now, when you think of satellite, I bet you think of the things that have all the high tech and they go around, they give you GPS and weather forecasting and all that stuff. Yes, that is a satellite, but a satellite is actually just something that orbits a planet, okay? So a moon is a satellite because it orbits the Earth, all right? And we call them a natural satellite because we didn't make it. It's a natural satellite. The things that we make are called man-made satellites. It's just something that goes round the Earth. And that's what a satellite is, okay? So, that's solar system. Nice and easy, good recap. I imagine you might have done that in primary school as well, or you might just know it. What we're gonna do is talk about space terminology and dive into a little bit more stuff, okay? So, first of all, stars. I love stars. Stars are amazing. My degree was actually studying stars, believe it or not. But a star, for you guys, is just a sphere of gas emitting light, heat, and other radiations. It is huge. It's quite hard to fathom how big the sun actually is, but it is massive, all right? And the heat that comes off that sun is enough to power the whole Earth, and it's millions of miles away. Millions of miles away. Exoplanets is a planet which orbits a star, but not in our solar system. So we've got our planets. Exoplanets are basically planets out with our solar system, okay? And then we have galaxies, and our solar system is one tiny part of a huge galaxy called the Milky Way. But our galaxy is just one part of an even bigger cluster of galaxies. That's just one part of even a bigger section of the universe, which is part of the wider universe. And you can just keep going. The universe is massive, all right? Absolutely massive. So we live in a very, very, very small corner of the universe, all right? And then the universe has a radius, as in like it stretches for 40 billion light years. Now we're going to talk about what light years in a second, but that is a very long distance. In fact, I don't actually think you can comprehend, because I can't comprehend how big that distance actually is, okay? So, it is everything we can touch, feel, sense, measure, or detect, okay? So everything that has matter is part of our universe. And as a little side note, there's also things out there called dark matter and dark energy that we do not see, that's also part of the universe. I'll keep that for anyone who wants to go and research that themselves, all right? So the universe is just everything that makes up the universe. That's what it is. Now, we know that we talked about a light year. We said that the universe was an X number of light years across. But what is a light year? Okay? So a light year, basically, space is so big that we can't just measure it in meters. I can measure the length of a classroom in 10 meters. Okay? But when I start to think about the distance between me and the nearest star, I get too many meters, and it becomes difficult to write it all down. So we actually use something called a light year. And the light year is just the time it takes, or the length that a light has covered in 1 year. Now, light travels exceptionally fast. Again, probably faster than we can even comprehend, but it goes so fast. Yet, it takes time for light to travel in space because the distances are so huge. So 1 light year is just the distance it takes light to travel in 1 year. That's all it is. Okay? So, we're going to use light years. And that's exactly what I've said. But let's calculate it out. Okay? Now, we're on page 10. So if you're on page 10 and following along, you can pause it, you can do all the notes, but we're on page 10 now. Okay? Now, we're going to do some numeracy. So what we're going to do is, you might be aware in maths from distance, speed, and time. Now, distance, speed, and time is a very easy equation, but we're going to put some information in here to give us the distance of 1 light year. Now, the speed, all right, the speed of light is 300 million meters per second. Now, that's fast. Okay, Usain Bolt ran an average of 10 meters per second. Okay, maybe just slightly under that for his world record. For us, this is again a number that's just beyond our understanding. It's so fast, all right? Now, we're going to use that for the speed though, that big number. That's how fast light goes, all right? But remember, light takes time to travel to places, all right? Because the space is so big and the universe is so big. So what we're going to do is we're going to calculate the distance. We've got speed, but now we need to find the time, or the number of seconds in 1 year. Okay? So, lots of things to highlight there. Make sure you know what those things are. But let's see if we can find out the time. So, to get a time in 1 year, we need to have 1 year. Okay, so we've got 1 times how many days are in a year. Now we've got 365.25 days. I wonder why it's 0.25. I wonder if anyone can guess when they're thinking about it right now. Do you know? Well, 0.25 is just the fact that we actually go slightly beyond 365 days every year. And that's why every 4th year we have a leap year, because we add on a day to get ourselves back into the rhythm of going round in a year. All right? So we have to make sure that happens, or else things would go out of sync. So 365.25 times 24 hours times 60 minutes times 60 seconds. And so if we add all that up, we get a large number. We get 31,557,600. So now we've got 2 big numbers. We've got 300 million and we've got this number here. What we're going to do is we're going to times them together. Okay? So if we times them together, this is the big sum that we have, and we get this number here, 9.5 times 10 to the 15 meters. Now, what does that actually look like? Well, here we go. That's basically this. It's 9, 5, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0 meters. Now let me just double check that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's how many zeros there are after that number. Okay? So that's a long distance. And again, that's so hard to understand. because we are only so used to such small distances in comparison. Now, let me just get rid of my pen. There we go. So the number it takes days in 1 year is defined as 365, and we said that because it's a leap year, okay? Now, we're happy with that, but let's look at some distances in space. Now, this is really interesting. I love this bit, okay? From the sun to the Earth, it takes 8 minutes for the light to get there, okay? Now, that means if the sun exploded right now, we wouldn't know for 8 minutes. We wouldn't know for 8 minutes because it takes time for the light to travel because the distances are so big, even though it's going so fast. Okay? Look, can we look at how big that meter is? The next nearest star, 4.2 light years away. Right? So that means that our next nearest star, when we look at it, that's actually 4 years ago. The light that we saw is from 2017. That's how far away it is because the light takes time to travel. Across the Milky Way, 100,000 light years ago. Now, I don't know what was happening 100,000 years ago, but you can imagine the light that we're seeing from the edge of the Milky Way, and you'll only be able to see that with really good telescopes. It's just a world away. We don't even understand. We can't understand that is such a long time that light is taken to travel to us. So if we look at that through telescopes, it's actually quite fascinating that we're seeing light from that far back in time. To our nearest galaxy, we're talking 2.5 million light years. We're getting to crazy understanding. See that? It's hard to understand 2.5 million years ago. If we look on a light, that star could possibly be dead now. That's how crazy that is. And across the universe, 93 billion light years across. Now that, I'm not even going to go into that because that is just too mind-numbingly hard to understand. Space is big, and that's an understatement. Okay? Right, last thing, telescopes. Page 11, let's rattle through this, okay? So the famous guy who kind of discovered telescopes in physics was Galileo Galilei, okay? And in 1610, he made many discoveries about the solar system using a telescope that he constructed, okay? But he was criticized a lot with his theory of the sun because it wasn't quite in keeping with the things that were going on at that time, okay? So this was contradictory to the popular belief that Earth was at the center. People thought that Earth was at the center of the solar system, not the sun. But we now know that the sun is definitely the center. Okay? Now, when we're using a telescope, we must never look at the sun because basically it's like a microscope. It takes the light in and it magnifies it. Okay? Now, if we do that and we look in with our eye, we're just going to damage our eye. So sometimes in specific telescopes, people put a solar filter on, and that stops you from getting damaged eyes. But it's incredibly dangerous to look at the sun with a telescope. So don't do it. Okay, don't do it. And that's what we've got there. Yes. Okay, so that's a modern telescope. This is a refracting telescope. You can see it looks kind of long and it has kind of a wee tripod. Now, I'll tell you this. You could buy this for 100 to 200 pounds. That's quite a lot of money. But I'm telling you, it's nothing compared to if you really want a good telescope, you're probably looking at about 1,000 to 2,000 pounds worth of a telescope. Plus, you need a really good computer to process all the information that's going on. So it's actually a very expensive hobby. And these ones are okay just to kind of go out and have a wee look at some things. Now, we see that there's an eyepiece lens. That's the lens that we look into. Now, a lens is just something that focuses light. All right, and so we can see things from far away up close. We have this tube that the light goes through. And we have this thing called the objective lens, which focuses light to produce an image of a distant object, okay? Now, you've probably seen a lot of photos of space. And a lot of those photos will have been taken by this thing here called the Hubble Space Telescope. So now this is a very fancy telescope, and not all telescopes work in the same way, all right? So some are in space, some are on the ground. Some look for visible light, some look for other forms of light, okay, like radio waves or gamma rays or x-rays, things like that, okay? And now, it's captured so many photos that have captured the imagination of so many people through this one telescope. It's fascinating. But that's all I've got time for to talk to you about telescopes today, all right? There's a wee link down here, and if you see it, go onto it because it has all the photos that the Hubble telescope has taken. And that'd be a really interesting thing to look at. Now, go through, you can pause it, stop it, fill in the notes, do all those little things here and there. But I hope that's interesting and a good first revision for part 1 of Key Area 1. And then we're going to jump on to Key Area 2. All right, S1 and S2, very well done, and I'll see you soon.